Okay, Dr. Ananthanarayan is a professor and former chair of the Center for High Energy Physics at the Indian Institute of Science. He obtained his B.Tech in Chemical Engineering from IIT Madras in 1985 as part of the last 5-year batch. Am I right?
Yes.
And in 1991, he took his Ph.D. from University of Delaware. And then he was postdoctoral in PRL, Ahmedabad, and University of Lausanne, Bern. He joined IISc in 1996 and has several areas of worked his research in elementary particle physics and field theory. He has involved in editorial work of Springer, and he has been nice enough to ask me to write a book. So I did write. Okay. So for over a decade, and then he was a Homi Bhabha Fellow from 2008 to 11. Is that correct? And was awarded Rustam Choksi Award for Excellence. And then chair of the Division of Physical and Mathematical Sciences, IISc. Ananthanarayan was the chair of CHEP for a second period of over 9 years. Okay? And 7 months. He is presently on Governing Council of IUAC Delhi and serves on the India CERN Task Force of the DAE and DST, and has been inducted recently into the advisory committee of the dual degree of IIIT Hyderabad.
Thank you very much. It's a great honor to be here. Let me begin by thanking the Tamil Nadu Science Forum and IMSc for inviting me, Mr. Vijayan, TRG, and Sita Brasina, and Varuni for all the excellent arrangements. It is particularly kind of important moment for me to be here because part of my interest in science came from my late mother, who was a teacher of science. And she, in turn, when she was young, she was influenced by her cousin, who was a founder director of this institute. So in a sense, I'm back here to repay my debt to this institute. We heard some very inspiring words from Mr. Vijayan and also from TRG. And part of this talk you will see is pretty much in the kind of ideas and the issues that they've already discussed, but I'm not going to repeat them. I do hope that you will hear the echoes of their observations and what I'm going to be speaking over here. So many of the issues, the social and the cultural issues that go hand in hand with science will also be part of this discussion, especially the interaction between scientists and society of this whole complex of philosophy and so on. So that's the kind of angle from which I'll be giving this talk. The reason why I've been giving this talk is over the years I discovered that practically nobody really is talking very much about it, with the possible exception in Tamil Nadu and a couple of other places. But definitely in Bangalore I did not hear much of this, because I was also invited by schools and so on to talk about these things. And then I had to do my own research. And most of the research that I did, actually, it was piecing together many things. So in fact, we have now a book in preparation with two of my former PhD students and Daniel Wheeler from University of Zurich. And we have a hard deadline of April 30th to finish it. So I do hope that we meet it. Otherwise, I don't know what to say. So let me dedicate this talk to the memory of all those martyrs to science, young and old. And let's keep in mind that your sacrifices will not be forgotten. And this has to do with those from the past as well as those who will be scientists in the future also. It's going to be a hard road to take, but that cannot be a reason for not doing it. So let me also begin with these very beautiful words. They are quite well known, and these come from David Hilbert, who was a very famous mathematician of the 19th century and early part of the 20th century. So he said these words: we must know, we will know. So there are two things over here. We must know is something, it's like an imperative. And the second part is even better, that through our own researches and our own struggles with the physical world around us, that we will get to know. This I find to be one of the most beautiful reasons for wanting to do science. And during the course of this discussion, we will also see how science is in a sense different from any other sphere of human activity, so to speak. that it will be subjected to tests that may not be the case in other spheres of human life, such as art or poetry or literature or human life in general, but science will have to obey certain rules whether we like it or not. I'm also going to show you this picture, and I'm going to ask you who this is. If you know, good. Anyway, I will not tell you right now because I'd like to tell you later. As was pointed out, the representation of women in science has been historically rather low. So this is a person who ought to be known, but is not so well known, although there's now an effort to kind of, accord the place in history for important persons such as this person whose name I'll mention later in the talk. So in order to describe what is science today in the third decade of the 21st century, we have to understand that it's a very complex procedure, a very complex phenomenon. It's not the kind of thing that we read about in textbooks about simple elementary things. It's very complicated. So for instance, let me show you this picture which was in the news a few years ago. This is something that comes from the EHT, which is the Event Horizon Telescope, and this was advertised as a picture of a black hole horizon. Now there's a bit of a problem here because a black hole by definition is something that you cannot see. So how is it that you can see something that cannot be seen? More precisely, this is consistent with the presence of a black hole somewhere in the center of this image, and this is matter falling into it, and this is consistent with the presence of such an object that is known as a black hole, a very dense region of space-time into which matter falls. And if there is matter falling around it, it can also get heated and emit X-rays and other parts of the electromagnetic spectrum, from which this picture is actually put together. This is a very complex picture. It takes data from many, many different observations and runs it through supercomputers before you can get an image like that. So that's the kind of thing that we are talking about in the 21st century when we are talking about science. And this is true in all spheres, whether it is biology, whether it is putting together the human genome, or whether it is looking at galactic surveys, or whether you're doing particle physics at the Large Hadron Collider, which is a subject of interest to many people in this institution. But I also want to bring in the human aspect all the time. It should not be something that's impersonal. After all, there can be no science unless there are human beings doing it. And what is the kind of human motivation that makes this kind of thing possible, and how does it go forward? So let me talk about one more dramatic discovery from a few years ago. This comes from something called the LIGO, which is the Laser Interferometry Gravitational Observatory, LIGO. So it actually consists of two stations in the United States, which are separated by many thousands of kilometers. One is in the southeastern state of Louisiana, and others in the northwestern state of Washington. So it actually has two stations. And I also saw in the guest house that there is a screen which has various things moving around. One of the things that was shown in the guest house here in IMSc was an animation of precisely this that I'm going to talk about. So we knew that this was going to be announced at a news conference, and at our center we organized a live webcast, and we were all crowded around and watched this. So this also makes things interesting to do things together. So when this news conference took place, the principal investigator of this project, David Rides, he said, we have detected gravitational waves. He was bursting with excitement, naturally. I mean, he was the principal investigator of a large collaboration and obviously had qualities of leadership. And he said, we did it. So these are such beautiful words. And this is, like the black hole that I talked about, is also another prediction of the general theory of relativity. And it took almost 100 years from the time of its prediction to the actual detection. In fact, Albert Einstein himself did not believe that gravitational waves would ever be seen, because in the era in which he lived, they did not have that kind of technology, that kind of sensitivity that would, render it a real possibility that this could be done. So it's an amazing thing that there are people who followed up this kind of an idea for 30, 40, 50 years. They showed such determination in order to go after something fundamental. Okay? Of course, we only always talk about the success stories. I'm sure there are others who are not as successful in their endeavors. And in this particular event that was seen at this, during when this was reported, what happened was that there were two black holes which merged, and the masses of these were 36 and 29 solar masses. And of course, any child knows that it adds up to 65. but the new black hole that was formed was only 62 solar masses. So what happened to the other 3 solar masses? So the other 3 solar masses went into energy, into gravitational waves. Can you imagine in a fraction of a second, 3 solar masses of energy being produced, which of course then shook the universe? I mean, just think of the scales of what happens in science, you know. The entire universe is being shaken. And this took place 1.4 billion years ago. Now 1.4 billion is a very special number for us Indians. Each one of us represents one part in 4.5 billion. So it is an important number for us. There are other kinds of phenomena which have also been seen now. For instance, they have seen neutron star mergers, not just black hole. And also now India will also join this, and then we'll have a station that's known as LIGO India. This was also mentioned in the finance minister's speech recently. From time to time, I'll also mention Nobel Prizes here and there, because as placeholders, because Nobel Prizes capture the imagination and make science popular, it plays a very important role. This doesn't mean that Nobel Prize is the only thing, or that it is really that important, but it's just a placeholder. For each Nobel Prize winning discovery, there may be 10 or 20 which are not going to win the Nobel Prize. But we're all human, and we do like a little bit of glamour, and things like Nobel Prizes, you know, ignite our imagination, so that may be one reason. So I also want to talk to you about the minds and the thoughts of some very well-known scientists, how they go about their project of pursuing science. Now, the reason for doing this is young people need to know what their academic predecessors did. How did they think about science? How did they embark on that path? Is it like studying for an exam? Obviously, it's not the case, right? So it also helps to read a little bit about scientists, what they do, provided they talk about it. Not all scientists do that, because many of them are very reserved and they don't think that it is their business to do that. But luckily for us, someone like Einstein, there's so much written about him, and he himself talked quite a bit, quite a talkative person, and he also engaged himself in matters of society, of war, of politics, etc., etc. Maybe a person of his stature could do that because he had no fear that it would affect his career or anything like that. So here he talks about how he chanced upon the principle of equivalence, and he said, I was sitting in a chair in the patent office at Bern. Now, some of you people have to wonder, what is a scientist doing in a patent office? Well, it so happened that he didn't always have a job, and it took him quite some time to find a job, partly because he was born in Germany, then he moved to Switzerland, he was stateless for a while, and while his papers were being processed, then he was a Swiss citizen, then he emigrated to the US. So his life trajectory also is a complicated one. So at a certain stage, he had to work in a patent office, and very often you may see a well-known picture of his standing at a lectern like this. Well, why was he standing at a lectern? Because I guess he was not given a chair, or he had to stand and he had to look at patents and inspect them. But the thing about working with patents is, I think he developed a very good sense of what will work and what won't. After all, he had to look at patents critically. So, and he also had a good sense of numbers, because you work in a patent office, you know, whoever's filed the patent will make all kinds of claims. So you have to check those numbers. So he was also very good at all these things. And while we always think about his great ideas, he also was very good at numbers. He actually calculated the rate of precession of the perihelion of Mercury and got the numbers right. So in any case, here he's talking about the idea of the equivalence principle. So he said that I did this simple thought experiment, and it impelled me towards a theory of gravitation. So, see, it is good to know how their minds work. Let me also show you some of the words from Chandrasekhar. There's another lecture hall in this institute named after him. So this is what he says about science, which I think is quite interesting. So he says, in some strange way, any new fact or insight that I may have found has not seemed to me as a discovery of mine, but rather something that had always been there and that I had chanced to pick up. Now, this is also an epistemological question, which is particularly important in mathematics, because there's always a debate about mathematical objects. There are many mathematicians here, and I hope that I don't talk total gibberish, but it's something that I'm willing to risk. So my idea is not just to, keep talking over here and expecting everybody to walk away with, agreeing with everything that I say, but rather to, stimulate and try to irritate you a little bit so that we can have a vigorous discussion also. So in mathematics, the question is, do mathematical objects exist before they've been found? by mathematicians, or is it just a figment of the human mind? Now, this is obviously a question that I cannot answer, that mathematicians and philosophers have to do. And when we are talking about the universe, which is what science is supposed to do, scientists are not supposed to be afraid of anything. We are supposed to be happy talking about laws at the smallest length scales or at the largest length scales. It's a kind of a wonder that the laws that we infer on Earth actually hold for the cosmos or at subnuclear scales. So here is, kind of a synopsis of the kind of length scales that we are dealing with. For instance, here is an oxygen nucleus, which is made up of nucleons, protons, and neutrons. But today, we know that protons and neutrons are composite particles made up of quarks, which we believe to be point-like, which then, forms molecules, which then forms a sand grain. And then here is a human dimension, which shows up here on a beach, and the beach lies on the coast of many of the continents. And this is where we all live. So this is the Earth. And this is where so much of science lives, the science of biology. This is the only planet that we know which supports life. There may be others, but we don't know. This is where climate science takes place. And then we also know that this object that's known as a pale blue dot. How many of you have heard this expression, pale blue dot? Pale blue dot, yeah. So this is Carl Sagan, the person who invented, which I find to be very beautiful because it also tells you, on the one hand, you're important. On the other hand, maybe you're not all that important. So anyway, so here's a pale blue dot that goes around this medium-sized star that is known as the sun, which is in this system that is known as the solar system. I'll also talk a little bit more later. But last week I gave this talk in ISI Calcutta in a building that was named after Kolmogorov, the great Russian mathematician. So you may wonder, although we have the laws of gravity which keeps the Earth in the orbit around the sun and the planets and so on, intrinsically this seems like it's a very chaotic system. But still, we know that this is stable, and it has been stable for a long time. So what does Kolmogorov have to do with this? Well, Kolmogorov has a theorem named after himself, Kolmogorov, Arnold, and Moser theorem it's called, which says that despite these systems being intrinsically chaotic, you may still get stable systems, which is a bit of a relief. Otherwise, I wouldn't be here talking to you. So anyway, that's so much for Kolmogorov. It also shows the importance and the power of mathematics that actually gives kind of a structure to the world and the universe that we live in. And this here lies in the outer arms of the spiral galaxy that is known as, what is this called? The Milky Way, yeah? So we need to relate to human experiences also. So how do we know that there are things like galaxies? Well, today we have telescopes, but already to our ancestors, there was a naked eye object that's known as Andromeda Galaxy, which they could see with their eyes. See? I'm not saying that you can immediately make the connection that we also live, but it's heartening to know that many of the things that we know today may also have been known to our ancestors. And this here lies in what is known as the local group, which is then sitting in this thing that is known as the cosmic microwave background radiation. So it's really an amazing story that today we essentially think that we understand many of these things and we have a structure to our knowledge. It doesn't mean that we've reached the end of the road and everything is known. Continuously find information about the universe. Now, so far I've talked about matter at the largest scales, so I should also talk about matter at the smallest scales. And in particular, of importance to people who work in the field of elementary particles is the discovery of a particle that's known as the Higgs particle, which took place in 2012 in a man-made experiment, a large man-made experiment where there's a collider whose circumference is 27 kilometers. Now just think about it. 27 kilometers is like twice the distance from here to the airport. And you're having an actual experiment. You actually have a device and a tube which is that large. And you have to be able to control the motion of particles in this using magnetic fields and electric fields and all these things. And one of the goals of that was to discover a particle that was predicted in 1964, a very good year, I might say. And it took 48 years for this particle to be discovered. So that's the kind of thing that happens in modern science, that you do something today and you don't know when it'll have an imprint. It's not like, Instagram or Snapchat or something like this. So you need a lot of patience in science. And this was due to, there was a Nobel Prize awarded to Francois Anglet and Peter Higgs for this particular discovery. The paper was by Anglet and Brout was an American physicist who was a thesis advisor of Anglet, but the paper was by Anglet and Brout. Now, isn't that amazing? That there was an era in which the advisor put his name after the name of the student, and this was not even alphabetical order. You have to think of how magnanimous this person must have been, that the student's name went before that of the advisor. So the reason why Brout didn't get the Nobel Prize was he had already passed away by that time. So, you know, the story is full of this kind of human element. Anglet himself was actually somebody who during the Second World War had to hide from the German invasion when he was in Belgium. So you see, so many stories behind every small thing, which can be of inspiration. So one need not think that, you know, life is so hard, it can always be much harder, and still you have to do what you have to do. I myself, as TRG so kindly said, work in field of elementary particle physics, and my interests also lie in combining mathematical methods to improve things like Feynman diagram computations and various other things. I'm just going to quickly flash one particular slide of a paper that we published some years ago with two of my former students. At the time, one of them was a current student, another former student, and my long-time French collaborator, Samuel Friot. So we were interested in certain integrals that show up and are closely related to Feynman integrals. And also the name goes under the name of Mellon-Barnes integrals. Mellon transforms are known in many branches of physics and engineering. And Barnes was the thesis advisor of Littlewood, who was the advisor of Ramanujan. So there's always a connection that we can find between what we do. So even though this looks like a paper in mathematics, it's of great interest to physicists. And we also had to write a code, and the referee also asked for the code before he or she allowed us to publish the paper. So we also, at this stage, got into the business of writing publishable codes, and we've had a lot of success with those. There are some words that I want to share with you, which is something that all of us have to deal with, us as in anybody who's a policy person or a member of society. What is this? What is it all about? What is this science all about? Is it really about technology? Well, of course, science will always go hand in hand with technology, whether we like it or not, and that's the way it is. So Robert Wilson, who was also a member of the Manhattan Project, then you will see that many of these powerful figures in science have, one way or the other, they're related to the Manhattan Project. So he was asked, he had to defend a project in the US Congress, and he was asked, what is this project good for? So the senator asked him, what is this, is there any technology associated with it? So, or making or good for defense. So he said only from a long range point of view of a developing technology. Otherwise it has to do with, are we good painters, good sculptors, great poets? I mean, all the things that we really venerate and honor in our country and are patriotic about, of course, applies to our country also. In that sense, this new knowledge has all to do with honor and country, but it has nothing to do directly with defending our country except to make it worth defending. What a beautiful speech, but the project was not funded. So that's the way it is. You know? So in this business of scientific discovery, the examples that I've tried to give somehow seem to suggest that we need massive teamwork and technology, which basically cannot be avoided at this stage. If you're a person working for ISRO or DAE or so on, you'll always have to work in teams. So you'll have to get used to it. Or if you work in, say, a company which does research, etc. But then this begs the question, what is your role as an individual? Are you just, one little gear in this big machine? Well, it's partly true. But then let's think about some examples where this is not necessarily the case, or whether we can learn something from what others do. The question that you can also ask is science really about reductionism, of getting to the bottom of things? Or is it so that there are sectors of science where there is no such fundamental law, but it's like you have to infer many different things, and then you have synthesis. Now, it's obvious in biology, today we are still not at a stage where we know the laws of biology at an atomistic level. We know many things and we put things together, and there's inference, and then there is, anecdotal evidence, or there may be statistical support for an idea, etc., etc. And these are not just abstract things. These things were very important at the time of the COVID business and about the vaccines and the efficacy of the vaccines, etc. When a problem is very difficult, the solution is also going to be very difficult. If you're talking about a disease that's going to affect the entire population of the world, evidently the solution is not going to be like writing a 2-page paper, right? Or finding the vaccine. So in science, we always have the struggle. What is it all about? But of course, the approach has to be scientific. You cannot be superstitious, or you cannot, just get away without lack of evidence or things being a matter of opinion. Of course, knowledge is also always incomplete, but you have to deal with that. But mathematics, on the other hand, is one field where it's possible to explain things even to young children and try to appreciate great things in mathematics, even obviously if you don't know the details of this. For instance, everybody in this room has heard of Pythagoras' theorem. We all know that 3 squared plus 4 squared is 5 squared, 5 squared plus 12 squared is 13 squared. Now, you have whole numbers whose powers add up to the power of another whole number. This is as old as history. It's there in every civilization. It has to be, because it also has to do with measurement of land, etc., etc. And human beings can relate to whole numbers. It's harder to deal with fractions, or even harder to deal with irrational numbers, or even harder to deal with complex numbers, etc. But integers, something everybody can deal with. An immediate generalization of Pythagoras, which one would have thought may have been done by Euclid or maybe by ancient mathematicians, only happened about 400 years ago, where Fermat asked the question, what about a different exponent? Why just 2? Why only squares? How many of you know the answer to this? Have you ever looked for whole number solutions to x cubed plus y cubed is z cubed? Can you raise your hands? Has anybody looked for these? Well, 0 cubed plus 0 cubed is 0 cubed, but that I don't think we're going to deal with. And we also don't account for negative numbers, so positive numbers. So this is like such a basic generalization of Pythagoras, but as far as we know, nobody did this, at least not in writing, until Fermat did it. He wrote it and he claimed he had a proof, which now nobody believes, that this is impossible for any exponent except 2. Well, yes, thanks. This is the TRG extension of the Fermat's last theorem. So he probably was able to prove this for a couple of cases in the 19th century. Many cases were done. In part of the 20th century, it was shown that you can have exceptions to Fermat's last theorem for all but a finite number of cases. But the actual proof only came about now 30 years ago, which is very recent, And this used ideas from earlier part of the 20th century, from Taniyama and Shimura. And these are guys who worked in Japan at the end of the Second World War. So you can imagine the conditions in which they must have worked. Nambu, who was also a Nobel laureate, he describes how he had to go to bed hungry many times, and he had to sleep on benches in the lab and so on. So that's a kind of struggle. But I should not give you the impression that suffering is either necessary or sufficient to make great discovery. But it's good to keep these things in mind. Okay? Now, the nice thing about Andrew Wiles is that he has also talked to the press, and there's a very nice BBC interview in which he talks about his eureka moment and so on. Another very great story from the recent past is this Poincaré conjecture about surfaces in 3 dimensions and their connectedness. And I'm happy to say that some of the ideas that Perelman used in his proof actually come from particle physics, from what are called Ricci flows, which actually had their birth in particle physics. So one of the key papers was by Daniel Friedan for his PhD thesis. So that led to Hamilton and then to Perelman. Now imagine, here it is a PhD thesis from Berkeley. It had no connection at all to Poincaré, but eventually it proved to give one of the important ideas. Of course, this Perelman, being a mathematician, is a little unusual, shall we say. He declined this prize, and then he also declined the Fields Medal. and I'm told he works for a software company right now somewhere. There is another subject which is well represented in this institute, which is called theoretical computer science. Now, can somebody explain to me how this is different from mathematics? Well, probably at coffee we can discuss. But to my innocent and naive mind, theoretical computer science is the same thing as mathematics, probably discrete mathematics. So there's a problem, and a lot of the material that I have is sourced from many different places. Quanta magazine, for instance, a very beautiful place where young people can read about constant reportage on new problems, breakthroughs, etc., not just in mathematics, physics, biology also. There's another one called ARS Technica. I think this is from MIT. And in India also we have people writing in Bhavna, very beautiful source to read about mathematics and so on. Then there's another one, Ganitasora from Assam, where people have been doing this kind of writing, and Resonance Journal. We are also, the people have taken a lot of interest in trying to explain these things. Yeah. Yeah, this is called the Caddison-Singer problem. This is named after Singer, the mathematician, IMsc. So the...
He's also a singer. He's also a singer?
No, I think that's
the name
his
is
name.
Singer.
And there's nothing to do with the sewing machine either. So, so this is a problem that was formulated in quantum mechanics initially. Then it was turned into a problem in linear algebra, and then into theoretical computer science. And this was solved recently, as in about 7 or 8 years ago. And it, again, believe it or not, has the name Ramanujan associated with it. Now, Ramanujan couldn't possibly have thought of Caddison-Singer or theoretical computer science. There was no such discipline in his era. But Ramanujan today is becoming somebody like Euclid, Some great idea, you say, is Euclid. So many ideas can be traced back to this wonder of nature who lived only to the age of 33, under whose nose I stand right now. I mean, can you imagine what kind of ideas he must have had, and what kind of insights and foresight he must have had, that his ideas and notions are being used over 100 years after his demise. This is actually very moving and touching if you think about people like this and how they did what they did. Yeah. So anyway, these are the authors who find the solution, and I'll also talk a little bit more about Nikhil Srivastava a little later. I should not again give the idea that all great discoveries are only in mathematics and physics, computer science. Well, these are subjects that I'm most familiar with, so that's what I can talk about. I mean, if you think of the periodic table, it's one of the greatest discoveries. Imagine organizing all the matter in the universe on a single piece of paper which hangs on every single college, every single laboratory. What kind of insight Mendeleev must have had. Or if you think of the theory of evolution, Darwin in that era, especially, he had to fight theological notions that it was a God who created everything, etc., for him to come up with this revolutionary hypothesis and to establish it. It's not just merely finding a hypothesis, you also have to establish it. I also consider things like Mendel's theory of genetics. I, as in a random layperson with an interest in science, Mendel's theory of genetics to be extraordinary, Although people may criticize him for having selectively used his data, many statisticians have looked at his data. They can suspect him, doesn't matter, his place in history, I think, is secure. I mean, to say, we all know that we have traits that we inherit from our parents, but exactly how does that work? So to have a scientific basis for that. Or Pasteur's theory of microbes, that yogurt, Thayersadam and Madras speak so important, as well as beer, equally important. Both have the same origin in microbes. Just think of that, Or other things like Shannon's theory, or the continental drift, or the ice ages, and this Milankovitch cycles. If you read about things like Milankovitch cycles, which has to do with various periods of the Earth's climate, there are cycles of 40,000 years, 100,000 years, and he was able to infer that this has to do with the eccentricity of the Earth's orbit, which is influenced by Jupiter, or the angle of tilt of the Earth's axis and how it precesses, and to link that to climate cycles. I mean, just imagine what an amazing thing that must be. As mentioned by Mr. Vijayan earlier, we also need to talk about women. So women, as we know, have been historically discriminated against for millennia, and yet we can, if you put your mind to it, you can trace many important ideas to women who have contributed in a very important way. Ada Lovelace today is considered as founder of modern computer science. I don't know exactly how, but there are experts here who can talk about it. Or M.E. Noether is considered as the founders of modern algebra. We all know about Marie Curie. And finally, I'm answering the slide number 2 in my talk. So this is someone called Cecilia Payne, who analyzed the composition of stars. We also can talk about Julia Robinson. She gave a solution to Hilbert's 10th problem, at least part of it, along with others, and linked it to undecidability, which is also another cornerstone of modern logic. Now, Hilbert had defined 23 problems in the year 1900, the first International Congress of Mathematicians, and that was to shape the development of mathematics for a number of years. Some of them were solved almost immediately, but others are still not solved. So this is to say that individuals do play a role in how science is shaped, and there's no reason for you to think that you can't be one of them. All the young people here should have that confidence, and then they should apply themselves and cross these difficult seas. Each time I give this talk somewhere, somebody will say, you left out somebody important. So I gave this talk in Calcutta last year, already a year and a half ago. Someone said, you have to mention Catherine Lonsdale, who was very important in the structure of benzene. So there she is. So many other examples, and I don't have to go through this entire list. So this Vera Rubin today is identified as essentially the person who established that dark matter exists in our universe. So in my long and painful tenure as chairman of the Center for High Energy Physics of 3,520 days, there were not many high points, but one of the high points was I got to have lunch with Jocelyn Bell when she was visiting IISc at the guest house, but don't tell anybody the lunch was not very good. So I don't know why we invite all these great people and subject them to such average lunches. Anyway, so many others, Rosalind Franklin and now many mathematicians. Two of them have won the Fields Medal in the last 15 years or so, and we also have leadership. Fabiola Gianotti, she's just stepped down as the Director General of CERN. She had 2 terms, and so many others. I also want to draw your attention to this last point, the last 2. Bibha Chaudhary by now is getting to be rather well known. Possibly she was essentially on the scent of the pion, 1935. And then there's a cousin of the pion with a strange quark, which is known as a kaon, and this was discovered by Rosemary Fowler in 1948. And I want to assure you that there's no typo on this slide. Does anybody see what the possible typo is? Anybody? She was awarded an honorary doctorate by University of Bristol in July of 2024. Okay, so it took them how many? 76 years to award the Ph.D. Okay, so don't get frustrated if you have a delay of 3 months. CSIR fellowship has not been paid, etc. I'm trying to make this kind of humorous, but I think I'm not having much of an effect over here. This is another key Nobel Prize from a couple of years ago, when both the laureates were actually women in biology. So I just thought that I'd put this slide over here. And then here are slides of some of the women that I had mentioned. Here's M.E. Noether and late Mariam Mirzakhani, who died tragically at the age of 40. And then there is Fabiola Gianotti. I only recently discovered that M.E. Noether's father had also been a mathematician. So I was wondering how come there are theorems named after Noether before she was born. Then it turned out that it's not M.E., but it's Max Noether. And someone also told me that she actually had to teach some of his classes because she couldn't get a job, because in Germany at that time they're not giving jobs to women. Eventually emigrated to the US, unfortunately passed away very soon. So one of the themes that I've been trying to say is that suffering is both necessary and sufficient. So unfortunately some of the stories that I have are quite tragic, but this one wasn't. She actually is about 98 years old, and she actually went to receive her PhD at that age. So I also want to just point out a little bit about Hargobind Khurana. He's one of the earliest pioneers as far as biology is concerned, and he went very early on. He went to the US, and he was one of the early Indian winners of the Nobel Prize, and we have just passed his centenary year. There are many, many other great Indian pioneers, many of whom come from the era before 1947, and so there's a problem in the narrative also that most of the great people we talk about are people essentially from before 1947, a little after, who are all people who built institutions, etc. But we also need a narrative about the here and now. Who are the living? Who are the people? Who's talking to you? Who's not talking to you? Etc. So, just here is an honor roll of some of these great people, our predecessors, J.C. Bose, Ramanujan, Raman, whose Raman effect we are celebrating today, Saha, one more Bose, S.N. Bose, Bhabha, and I was just the other day in the ISI, and I mentioned Mala Nobis and the Indian Statistical Institute, and someone said you also have to mention that there's a distance named after him about correlations, which is very important. All these are well known, but the last one who ought to be well known is not so well known, and he's got a mention in this book that's called The Emperor of Maladies by Siddharth Banerjee. It's a very beautiful book, and I didn't know. I knew Yellappa Rao had actually was a pioneer in some antibiotics, but I didn't know that he was also a pioneer in chemotherapy. So it's very important for us to know who all these people were, because they may be inspiring for us and to also restore their place in history. Many other institutions that we have, many other people, many great people, but the point is you don't really find very much biographical material on many of these people. One of these efforts that I know was by G. Venkatraman, who used to be in Kalpakkam, who's written small books essentially to motivate small children, young children. So, these are all some of the great people that I wanted to mention, some of who are unknown, partly because the areas in which they work were so difficult that others cannot really follow what they were saying. So in the last few minutes, let me tell you about, I promised you in the beginning to say how science is different from other subjects. Well, whatever you consider scientific is something that has to be true irrespective of where you are or when the scientific discovery was made. So it has to obey certain rules and has to pass certain tests that other things don't have to. Somebody may consider Picasso to be a great painter, somebody else may say, I don't like anything, and you can't contest that, it's a person's subjective choice. But in science, you have to be objective, there's no other way. So how do you go through this process of becoming a scientist? Well, I'm not the first to have thought about this. Jacques Adama, he's written a book called The Mind of a Mathematician, where he talks about many of these ideas of how a mathematician goes about the process that he calls preparation, incubation, illumination, and verification. And there's also Helmholtz has talked about it. Anybody here heard of Helmholtz? Helmholtz equation, Helmholtz coil. There's also Helmholtz free energy. I didn't think energy was free, but anyway, he's a lucky guy. For him, energy was free. He is also the one who invented the ophthalmoscope. Just imagine, this guy was also a professor of physiology besides being a professor of physics. I'll be done, don't worry. So there's a sequel to Adama now by David Bessis, where he also talks about the way in which people think about science, the process of learning. So this I recommend to the young people. So there comes a time when you're dealing with whatever it is that you're doing and suddenly you get an answer. You get, for instance, Planck has talked about how he hit upon his radiation formula and how he had to basically formulate the quantum theory. Poincaré, he's also talked a bit about the psychological processes. So he talks at length actually about his eureka moment of how he was stepping on to an omnibus and then the solution to a problem he was working on. So there's a period in which you have to think very hard and then maybe your mind needs to relax and then you get the answer. This essay of his is actually reproduced in Resonance and you can get it from Google. There are others also who speak of their eureka moments. Kekulé, there's a famous story of how he saw a snake eating its own tail. Max Planck has talked about it. And scientists, of course, work very hard for this moment, which may or may not come. I also have had a couple of such moments. Here is a preview of my autobiography, and you can read it at length about it. I shouldn't only be quoting people from long ago who are all dead. I should also quote people who are young and who are still here and necessarily much younger than myself. This Nikhil Srivastava is one such. I have not met him. He used to be in Microsoft in Bangalore for a while. He's gone off to the US. So he talks about the need to work hard, but he also advocates having to take time off. This is what they call work-life balance and all those things. And he makes an important point that sometimes problems may not have a solution, and that's just so. You have to move on if it doesn't work. Venki Ramakrishnan, another great guy, he's also talked about it. He was also president of the Royal Society, etc. He makes a point that it takes courage to tackle very hard problems in science. Now, I'm beginning to make the sound as if science is so difficult that, nobody can really make it. Well, if I have, so can you. So I don't want to scare any young people over here. And he also makes a point, which I think is important, is science should not be converted into a contest. I personally don't like all these hackathons and contests and Olympiads and all these things, but who am I to say? Maybe there is a place for this also. But in any case, if you don't do well on those, it doesn't mean anything. You may still be a very successful person later on. Weinberg himself has given a few golden lessons, essentially consistent with what I'm saying, that no one knows everything and you do not need to know everything to start doing research. Anybody can start, provided you have some basic knowledge. He also says aim for rough water, which is to say that you're not to work on just, small extensions of known things. And he says, forgive yourself for wasting time. I don't think this is very good advice, but anyway. And he also says, learn something about the history of science. I think that would help. And for young people, I think today, communication skills are very essential. You could, of course, take help from ChatGPT and Grok and Claude and whoever, but of course, you have to develop it itself. I mean, all these things, they also write garbage, right? I mean, you just give some keywords and may give something that sounds beautiful, but maybe totally wrong. So your mind also has to be behind it. And there have been times when many good papers, good scientific results have not been recognized because the person has written the paper so badly that the reader has not appreciated what he or she has done. So I think communication is a very important thing, and it is transforming on a scale that we cannot even imagine. It's just too much. In my opinion, and this is not often something that in India we talk about, I think we all need to talk to people from other spheres of human life, poets, artists, how do they create. You'll also be surprised at how much they know. After all, they are also people who have to create, they must have a product or a deliverable at the end of this. And one thing that's inevitable is that no matter what you're trying to do, there's something called cognitive stress. In trying to learn anything new, there is stress. It's not a walk in the park, unfortunately, and that's how it is. But for young people today, it's part of the target audience here, there are so many places in India today where you can have a fulfilling life as a student, as an academic. We have all the IITs, IISers, universities. However, nobody in India really talks about what they actually do. Very rarely do they talk about what is their discovery, why is it important. There was one counter-example from some years ago where I think even Frontline had a very good article on this discovery of Agarwal, Kayal and Saxena, again theoretical computer scientists. It was like a very nice detective novel, how they went through this process. One of my late colleagues, your father's colleague, Anil Kumar, NMR, you must have known him. He has actually written a very nice article where he discusses how he found an important effect that's known as a nuclear Overhauser effect in biological molecules. He gives a whole story of how he needed to use a machine, and the period between Christmas and New Year, he was the only user of this machine because everybody else was on holiday, and how he made a few mistakes and eventually got the answer, and then this became one of his most important discoveries. There are very few such stories, very few and far between. So it would be good if people in our midst, all the scientists and mathematicians and computer scientists, tell us a little bit of what is their most important discovery, how did they do it, and what are the struggles, etc., etc. Yeah, I don't do it because my work is not important enough. So anyway, let me conclude by telling the young people here that you have to follow your hearts. If this is something that attracts you, just do it. You just can't all the time have an answer, what is the ROI and what it is that I'm doing, you know. The ROI is your own joy that you discover when you're doing something important. And for a society, unless there is research, there is no future, okay. So the society will stagnate. And we have to keep in mind the words of people like Edison, who spoke of genius as 99% perspiration and 1% inspiration, although I think he was wrong. It's probably more like 99.9% inspiration and 0.1% inspiration. I also want to refer you to this article by Richard Hamming, who is also in the Manhattan Project. It's a very nice speech. It's on YouTube. There's also a transcript. You and your research makes many, many important points on how you deal with being in an organization. And I don't want to give away the plot. You can have a look. Of course, we also say that X was lucky and Y was lucky. So, but what is luck? I mean, you need a definition. Again, luckily for us, this was already defined over 2,000 years ago. Luck is what happens when preparation meets opportunity, which means that you have to be prepared so that opportunity falls into your lap and you can seize the moment. Let me more or less end with this, what Charles Darwin says on his theory. So he's talking about biology, which is at the other end of physics in terms of complexity. That there's a grandeur in this view of life with its several powers having been originally breathed into a few forms or into one. And that whilst this planet has gone cycling on according to the fixed law of gravity, which is very simple. From so simple a beginning, endless forms, most beautiful and most wonderful have been and are being evolved. So he's talking about the structure of biology. You know? So let me now end with these words of David Hilbert again, this time in German, sounds so much more noble. Wir müssen wissen, wir werden wissen. We must know, we will know. Thank you.
Thank you very much, Anant. It's a fantastic talk and exactly on 45 minutes time. Thank you very much. Before I throw open the thing for the question, I should have done right at the beginning. There were 3 speakers in that list of 107 actually, who are no more with us. One is G. Rajshekharan, who was the joint director of IMSc initially, later professor, senior professor, and also emeritus professor. He was connected with the neutrino physics. He was also very passionately working for creating the INO, the neutrino observatory in Theni. Unfortunately, he didn't succeed, but he has been always associated with Science Forum, and he was also one of the first speakers in 1981, but later in our time itself, he did give a talk. Second person is Rajaraman, Professor Rajaraman from JNU. He had come to Science Forum twice, and he did talk about his favorite later subjects, mainly nuclear issues, questions, and disarmament. And very interesting, and he is also no more. The last one which I should mention is Rohini Godbole, who was from Center for High Energy Physics. She has also come and talked. Was it online or? Online, because during the COVID period I had to... Yes, Steven Weinberg. Yes, about Steven Weinberg. She did talk to us, and she was also one of the persons whom we are missing in that list of 107. And now the floor is open for questions. We'll take 10 minutes and then 11:30 we'll go for coffee. Please, go ahead. Anyone who wants to ask.
Firstly, good morning, sir. I'm Revant from Madras Christian College. You told us to start reading research papers. Which ones would you prefer to read first, or what kind of papers? So, do you want us to read first for beginners?
This Quanta magazine and ARS Technica, for instance. So you have to read quite a bit, and you see what captures your interest. That would be one starting place. Another, of course, you would have to talk to your teachers. or you would have to come for an occasional lecture at a place like IMSc, where you'll have the world's experts visiting and talking about the latest amazing results.
Thank you, sir.
Yeah, we do organize colloquiums, and usually they are for all the audiences more than the experts themselves. We would
There's
like
no
to-
shortage of resources. You can also have a physics club, and you can invite people to come and give talks, etc.
Okay, others that want to rise? Yes, go ahead. Students particularly.
So this is Vidya. When you were talking about the journey of how the mathematicians is not being recorded, I recently happened to see a book about William Dunham, The Journey of a Genius, where he has elaborately talked about how Isaac Newton or Lewis Carroll, all we know is about Alice in Wonderland, but the other phase of Lewis Carroll being a mathematician and how he developed mathematics and poetry was kind of eye-opening. I would like to know, when you are talking about Indian scientists and mathematicians, do we have such kind of a history itself for us to kind of know about how they developed such a kind of passion and the process of becoming a mathematician?
Yeah. So we have to look at many different eras. One is, let us say, pre-modern mathematics. Now there is a lot of work being done on Kerala School of Mathematics, all these things. But we don't know anything about the individuals. Late P.P. Divakaran from here, he has just written a book published by Springer that you can have a look at. But that's about the mathematics. We don't know anything about the figures. You may say Aryabhatta, Bhaskara, we don't know anything about them, whether it was even one person, or if you say Agastya could well have been a seat that many individuals occupied. So when they say Bhaskara, probably there was a historical person. So that is one era. In the recent era, we can probably date it to post 1857 or so with English education. Then we can start. If you look at the life of Ramanujan, you will see many figures associated with him. There's one Ramachandra Rao who encouraged him. Then one of the earliest books on topology, which was in Russian, was translated by an Indian mathematician. What was his name? I've forgotten his name. It's some Vaidyanatha Swami. He is the one. So there are identifiable individuals about whom we know something. Veera Raghavan was another. Meenakshi Sundaram, many from here are people about whom we know. But Meenakshi Sundaram also died early. He never wrote his autobiography. He was probably busy with his equations, and then one fine day he's gone. This Bhavna magazine is very amazing. The people who work and write there, and it's a tireless effort which has been going on. I find it really incredible. Bhavna, it's available online, you can have a look. There must be others, but yeah, there must be others. I'm not saying that there's nothing. All I'm saying is that there probably isn't enough. We have to capture the minds of millions of people, and if it is in English, you're not going to reach people who are not literate in English. So to be a citizen, one part in 1.4 billion of this country is already pretty complicated. With all, you see, the example of Isaac Newton you mentioned. He is lionized, and his biographies and all British have made a great thing about him. The French are very good at writing biographies. We have not been as good. We have been a poor country. Everything requires resources, right? You need a department of history, you need people who can read archival material, who can write a sensible biography. It's not just a hagiography where you say, oh, this guy is great, that guy is great, but you have to demonstrate what is the greatness. So it's a project, and perhaps industries can start giving fellowships to people, give somebody a 5-year fellowship, somebody wants to investigate the life of Harishchandra, somebody wants to investigate the life of B. Anantanarayan, sure, they should be given money to do that, Of course, this may be just 2 pages, so.
So I have a comment to make. Firstly about Bhavana, and a review by Amritanshu Prasad of a book, biographical book by Chandrasekhar Khare. It's called Chasing a Conjecture.
Yes.
And it's something that's, I think, far more elaborate than a case, they have, mentioned about Kayal I don't
Yes,
know if
yes, yes.
This book is far more elaborate about the discovery process.
Okay.
It's one of the best. He's a great writer, and Amri has done a great job of the review also.
Yeah.
And it appears in Bhavna, so it's connecting all these three things that you mentioned.
It's very recent. I saw in the newspaper
It's
the
recent,
mention.
it's about 2-3 months.
Yes,
And I think there are some interviews by Shekhar on this as well, which appeared maybe a month ago. But anyway, yeah, it's out there too.
Yeah.
You can search again, Chasing a Conjecture by Chandrasekhar Khare.
Yeah, thank you. I mean, even people like Kosambi or Abhyankar, hardly known in the public mind. There's no knowledge of these people. I mean, mathematicians may know, but others definitely do not know these people.
No, I actually just wanted to highlight Bhavana. Every issue of Bhavana has an in-depth interview with a mathematician. And these are very nuanced discussions. It's not just about prizes and recognition. It's about how these people grew up, how they learned about mathematics, how they became mathematicians. So I think this will really, what you're looking for in terms of the personal lives of mathematicians, how they got there. And it's not always that simple, and each story you'll see is very, very different. So I'd really encourage you to subscribe to Bhavana and look at it. Of course, I have no personal profit from this. I'm just saying that this is really something amazing, and there's a lot of Indian people. It's not an exclusively Indian thing, but a lot of Indian mathematicians are featured in this.
In fact, in one of those interviews by V.S. Varadarajan, he has a very moving passage in Bhavna, I think. He says, every one of us has a family, every one of us has problems, every one of us has responsibilities.
Yes.
We still have to do what we have to do. In a sense, it's a tautology, everybody knows it. But when someone like Varadarajan says it, it has a certain gravitas to it, so it's worth keeping in mind.
Okay.
So thank you very much, sir. What is the physical dimension of the black hole, sir? And what is the distance? How many light years is from Earth? Can you tell me, sir? If you don't mind?
There's a whole family of such black holes. There are microscopic black holes, there are massive black holes, solar mass black holes, there are objects called supermassive black holes, which may be of the order of 1 million solar masses. Our galaxy is known to have a supermassive black hole.
Okay.
The dimensions of these are fixed by something known as the Schwarzschild radius, which was worked out 1 year after Einstein's theory. It's pretty amazing. Carl Schwarzschild already worked it out. It's a static black hole. If it's spinning, it's somewhat different. But it's known. Depending on the mass, it's not called a dimension per se, but something known as a distance that you can associate with a black hole that's named after Carl Schwarzschild radius. So I'm sure if you go to Wikipedia, you can find a table of mass versus Schwarzschild radius.
Sun has typically 10 kilometers. So
pretty
if you know the mass in terms of sun, multiply by 10.
Thank you.
Okay, go ahead.
Thank you, sir, for explaining the everything about the science, and also thanks for witnessing that about the women achievers in science. And now I have a doubt, like, about the Rosalind Franklin and all. I used to study my prescribed book in my college, but there is only one line about her, like she discovered this, and the male about the other scientists, they have about the scientists, they are given pages of lines. Now I thank my lecturer Aarti ma'am. She only told the history of Rosalind Franklin, but how to make the history accessible to all? Like, everyone should know the history of the achievers, right, sir? So
Okay.
I thank you for placing here. So.
Okay.
I'm attending the lecture here, and I know about, I have an opportunity to know about her, but how others can be accessible to that, and it should be accessible, right, sir?
Okay.
We can only do what we can. I give a talk, you write an article, you spread this word. And Rosalind Franklin, of course, tragic story, she also died early and all these things, and that's how it is. Jocelyn Bell didn't win the Nobel Prize either, but she got this Frontier Prize a few years ago. So what can one say?
Okay.
That's how it is, and you just do the best that you can during your lifetime to correct what you consider as
You can sit down, This
as
one
something that was not
This is
correct.
not a classroom.
It is a continuous process. It's unending. I'm going to write a book
Okay.
for which I have a deadline. Tomorrow you write one.
Okay, last question. Here.
Sir, actually, I recently read this book by Robert Canigal
Yes.
on Ramanujan.
Yeah.
So I came across something called mock theta function.
Yes.
So is it related to this gravitational waves? And you have mentioned that there's some loss at some 62, 60, like 65, 62 you mentioned in the beginning, the
Yeah.
bandwidth system.
Yeah.
So can it be related to that mock theta function of, I just wanted to know.
See, there are these black holes which string theory people study. There are people here also. In string theory, there are black hole solutions which get related to some of the work of Ramanujan. So there these mock theta functions may enter. I don't know directly whether in these things, but I can surely say that in the ring down from 65 to 62, the work of C.V. Visveshwara was very important in seeing what the daughter black hole was. That's an important contribution. Then there's Bala Iyer in Raman Institute, retired, has done very basic work for all this gravitational waves. And Sanjay Durandar from IUCA is another person who has done very important work. So Indian scientists have contributed a lot, and then we have a LIGO station now. So.
Thank you,
Okay,
sir.
thank you. I think probably we should close for the session.
Yes.
We'll go for coffee. A minor comment, you didn't make any remark about Bernard Riemann, outstanding mathematician.
I should.
Yeah.
I
No,
should.
don't bother about it. Don't bother about it. Okay.
It's an endless list. Yeah.
Okay.
Thanks. I will include it in the next,
Sure,
the next
sure.
edition. Yeah.
Sure.
Thank you.
Thank you.